In this video, we'll look into how to design a NAND gate using NMOS pass transistor. Here is a simple circuit schematic of a NAND gate. Right now, the gate terminal and the input terminal are not assigned with any variables. Let us do it from the table. In order to determine the gate terminals and the input terminals, first we have to write the truth table of a NAND gate. Let us do that. We have two inputs A and B. So with that we will have four combinations 0 0, 0 1, 1 0 and 1 1. And F is nothing but the output, which is nothing but the output of a NAND gate. It is just opposite of AND gate. The first step that we have to do is to choose the column B. Whenever we find a 0, we have to replace that 0 with B bar. Whenever we find 1, we have to replace it with B. Similarly, we have to choose the column A, and in column A, wherever there are zeros, replace those zeros with A bar, and wherever we find 1, we have to replace it with A. F column, let it be as such. First, let us replace A and B column with its respective A bar and B bar variables. It is done now. Next step is to group these signals. First, we are trying to group the first two rows of the truth table. Here, B bar, and on the next row again it is B bar. What is the output with respect to B? Both are 1. Let us now compare this output F with A. If it is A bar, the output is 1. Even though the input is A, again the output is 1. So, this particular value A is not going to affect the output whenever we have the control signal B bar, because whenever B bar appears, the output is automatically 1. So therefore, we can make this B bar as a control signal. So we are writing B bar here. What we need at the output? 1. This is a pass transistor. Whatever is in input will be the output whenever we have the control signal switching on the transistor. Therefore, if I want 1 at the output, it should be at the input again. Therefore, I am putting 1 here. So, B bar is the control signal, 1 is the input. So, with that we'll try to write an equation for one transistor alone. So, F, which is the output, it is equal to B bar into 1. Now, we have to allocate variables for the next transistor also. For next set of transistors, choose the other two rows. Now compare, both are B. What are the outputs at F? It is 1 and 0. Now let us compare this F with A. If it is A bar, actually we should have inverted output, but we are having 1. What is A? It is a normal value. If it is 1, actually it should be 1. But output is inverted. What it shows? When A is 0, output is 1. When A is 1, output is 0. Therefore, this shows that we are getting an inverted output of A. So, take that content to the figure. Control signal is B. Our output should be inverted value of A. Therefore, we are giving A bar as the input signal. Now, let us finish the expression by taking these two variables alone. So, I am making out a plus A bar into B. This becomes the expression F is equal to B bar into 1 plus A bar into B. Just multiplication of these two terms. Right now, I am taking this expression into the box shown below. Anything multiplied by 1, you can neglect the term 1 and write this variable alone. Therefore, F is equal to B bar plus A bar B. We have to use some theorems that we have learnt in our digital circuits to reduce this expression and see whether this expression is equal to the expression of a NAND gate. So let us take this into another box. where f is equal to b bar plus a bar into b. We have to use distributive theorem in order to expand this expression, where b plus b bar into a bar plus b bar will be the expanded form of this initial expression. 0 plus 1 or 1 plus 0 both leads to 1. Therefore, b plus b bar leads to 1. What the other half of the expression has? It has a bar plus b. Therefore, at the end, we will be having only f is equal to a bar plus b. Right now, for a NAND gate, what should be the expression? If it is a into b, it is an AND gate. If it is a into b the whole bar, it is a NAND gate. Now, here is the expression a into b the whole bar. If you want to make out a bar here, that is invert the complete output, we have to invert on the input side also. Only then the value will be equal. So I am assuming f bar equal to a b whole bar. Let us apply De Morgan's theorem now. What is De Morgan's theorem? If you have two variables, you can break the line and change the sign between the two variables. So if it is written as a b, it is assumed that there is a dot. What happens if you break the line? It becomes a bar plus b bar. That a bar plus b bar is nothing but the expression here. So if you invert this signal, we will be obviously getting your NAND gate output. So this is how you have to design a NAND gate, assign variables to the gate terminal as well as the input terminal, obtain the expression, reduce the expression and verify whether this is the expression of a NAND gate. Hope the explanation was clear. Thank you for watching.